Now we're going to learn about something called move semantics. What we've just done in the last lesson was we've developed this concept of a smart pointer because we want to place objects, whether they be large objects or dynamic objects, on the free store and store them outside of the runtime stack. And so we need a way to manage those resources properly. So we've developed a memory managing data type called a smart pointer, which knows how to create an object on construction, delete an object on destruction, and most importantly, because of the rule of three, it also knows how to correctly make a deep copy of the object on copy construction, and it also knows how to make a deep copy of the object on copy assignment. Okay, so that's great. Everything is completely functional, and we could get along just fine with this smart pointer. However, this smart pointer is not at all efficient because there are several scenarios. So if you think about it, we've focused on making a deep copy because that's the appropriate semantics for the copy constructor. But there are in fact many cases when a deep copy is not needed. Okay. Now remember when we just made a shallow copy naively like we were doing before, we ended up with segmentation faults. And the reason we ended up with segmentation faults is because we kept trying, after we had made that shallow copy, we were holding on to two objects which referred to the same underlying data, and then treating both of those objects on equal footing. The idea behind move semantics is that if you know for a fact that one of those objects is not ever going to be used again, you can optimize that deep copy that you would normally have to do. And instead of doing a deep copy, you just do a shallow copy, with the caveat that in doing the shallow copy, you reset the state of the object you're copying from so that it's no longer valid, or it's still valid in the sense that it's still a valid object that can be used in your program, but it's no longer referring to the same underlying data. In fact, it's not referring to any underlying data at all, if that makes sense. So the reason it's called move semantics is because it's as if you're moving the underlying data from one object to another object. And not just any underlying data, but specifically the resource. Okay, we're talking about memory resources, for example. When we have a pointer, for example, to a resource in memory, a block of memory on the heap, move semantics is the idea that you have a smart pointer referring to it and another smart pointer that you want to create as a copy of the original smart pointer. Rather than having two deep copies and then copying the underlying data, you're just going to go ahead and move the data from the first object to the second object. That's what move semantics is. So it's not just a shallow copy. It's not just saying, okay, let's also implement a shallow copy. No, it's a shallow copy where you are removing the data from one object and adding it to another object. And when are you going to do this? You're only going to do this when you specifically know that you don't need one of those objects anymore. For example, we looked at copy assignment. If I assign from object A into object B and I know that I don't need object A anymore, why do the full deep copy when I could just move the contents of object B into A via shallow copy and then throw away object A? All right. Hopefully that makes sense. So what I'd like to do is show you that move semantics is actually something that already is implemented for several data types we've been using, in particular string. Okay, and we're going to look at it with copy constructors. So we're going to create a string called data and print out its value. It's going to be data. Okay, we're going to copy construct a string based off the original string. Okay, and you'll notice that we will output both of those strings and see what the result is. We already know because we've done this several times. Okay, they're both going to have the value data. But then what we're going to do is something interesting. We're going to do what's called a move construction. This is different than a copy construction. And you'll notice you see this interesting function call right here called standard move, std move. So when we do std move on the original string and pass that to the constructor, we're actually going to call a special constructor called the move constructor. And the move constructor is going to do that thing we just talked about, where it's going to just, steal the contents of the original string. Okay, and then we're going to print out both strings and see what we get. So let's go ahead and run this program. I think you'll find the results are interesting. Okay, here we are declaring the original string and printing it out. And so that's what this line is right here. The original string is data. Okay. In the second section of code, we're just doing a copy construction. And so when we copy construct the original string into copied string, the original string is still data and the copied string is also data. Okay, now this is the interesting part. We're going to do a move construction. So we have moved into string and original string, and we're going to print them both out. And notice that the original string is now empty, and when I print it out, nothing prints. Okay, I am printing original string, but there's nothing there. It's an empty string. It's a string with no characters inside of it. And then moved into string, I print out moved into string, and it has the value data. Okay, so the string class actually does implement the move constructor and allow us to have move semantics. So how does all of this work, right? So what exactly is a move constructor? What does that even mean? Well, in order to understand a move constructor, there's one other concept that I need to introduce, and that is the concept of an rvalue reference. So we've heard about references before. Okay, so what is this rvalue reference? Well, the whole thing here with this idea of move semantics is that we know for a fact that one of these objects is no longer needed. Okay, so is there a way to refer to an object in such a way that the compiler can understand that we as program writers are aware? Like, is there a contract we can have with the compiler where we say, hey, this specific piece of data is no longer needed? Okay, and so that's what rvalue references are for, essentially. Okay, so to take a little bit of a closer look at what an rvalue reference is and the whole idea of move semantics, again, an rvalue reference is just a temporary value. It's a value that we're letting the compiler know that we don't need this value anymore after this line of code. So right here, we're creating a regular value, a regular variable, a regular string called a. Okay, and we might write some code that does a bunch of stuff. In particular, we might call a function. Let's just write a function called process string, which takes a string by value called arg. Okay, and it does something. It can just do nothing. That's fine. We're passing a string to this function. So we can go ahead and invoke this function, process string, and pass a as the value to that string. So maybe a little bit later in our code, we decide to call process string again, and this time we're just going to pass hello directly to that function. Okay, so is there a difference between passing a and passing hello? Well, there is. See, a is a variable which has a specific name. So kind of one of the ways you can think about the difference between a regular reference and an rvalue reference is whether or not something has a name. A has a name. Okay, the variable lowercase a is the name of some string, and we're passing that to the process string function. On the other hand, the second time we're invoking the process string function, we're passing this string hello, but what's the name of this variable? This variable has no name, right? There's no way to use this particular string inside of the main function after we've called this after we've invoked this function and passed this string hello to the function. There's no code I can write right here that will use this string hello because I have no name for it. There's no variable or no reference to that value. Okay. Now there is a reference to a because a I've declared in this scope. So the string hello is what we call a temporary string. It's only used on this one line of code. After this one line of code, there's no more use for it. Okay, so it's temporary. The variable a is not temporary. I use it on this one line of code, and then I can go ahead and use it later on, and that's fine. I can use it later on because it wasn't temporary. Okay, so when you see these words, when you see this standard move function being called, what this does is it converts a regular value to a temporary value. Okay, and I want to point out that I'm saying temporary, and that is the same thing as saying rvalue reference. Rvalue reference is synonymous with temporary. Okay, so now that I've made my string a temporary, it's the same as hello. Now I know I have a name for it, right? I just said like something that has a name is not temporary, but after this line of code where I have said standard move of a, I've converted it into an rvalue reference. And once I've done that conversion, I should not use it anymore. Technically I could, okay, I could try to use it, but the compiler will have been working under the assumption that I don't need to use it anymore, okay? And because I told the compiler right here I don't need to use a anymore at all, you'll notice that when I run this code, and try to print out the value of a, nothing is printed. It's just an empty string. It's an empty string because when I called move on it, the compiler treated it as a temporary and was given permission to reset its value. Temporary objects are objects that either don't have names or they had a name and they were useful in the past, but after a certain point in time, we're telling the compiler we don't need them anymore. And after you call standard move to convert an object to a temporary object, you really shouldn't use it anymore, okay? Because you need to work under the assumption that it's no longer containing useful state. It will always be valid, like it's not gonna like throw a segmentation fault if you try to use it, okay? But it will, as you see with string, it'll have been reset to an empty string. All right, so there's always some like way of resetting an object into some sort of default state when you move from it. All right, so all of this is to say that there is this concept of move semantics where you take advantage of making a shallow copy instead of a deep copy. But there's a caveat. You have to understand that you can only make the shallow copy when you know the object you're copying from is temporary and can be thrown away. Otherwise, you'd get the segmentation fault that we've been witnessing earlier, and we don't want that.